In this video, I'll talk about the concentrations of solutions. So we learned the solubility. That's how many grams of solute can be dissolved in 100 grams of the solvent. There are other units. The most commonly used unit is molarity. It's the number of moles of solute dissolved in 1 liter of solution. So we're talking about the volume of the solution. The shorthand notation is uppercase M. Again, it's the number of moles of solute per liter solution. So if you dissolve 2 moles of A in 5 liters of B, the molarity is 2/5. And we say it's 0.4 molar. The second most commonly used unit in chemistry is molarity. It's the number of solute dissolved in 1 kilogram of solvent. The shorthand notation is lowercase m. Again, it's the number of moles of solute per kilogram of solvent. Why do we need these two different definitions, different concentrations? The first one is really convenient. So you can easily measure the volume of the solution. However, remember, the density of the solution may change with temperature. So this molarity may change if you increase or decrease the temperature. Usually when you increase the temperature, the volume of the solution increases usually, and then you will have a lower molarity. So that's not very accurate. So if you say it's 1.000 molar, and then at a higher temperature, it could become 0.999 molar. All right. Fortunately, this molarity does not change with temperature, and this is accurate. The mass of the solvent never changes with temperature. So you just need to weigh the solvent carefully. You need to compute the number of moles of solute carefully, and then you will get this molarity accurately. It does not change with temperature. And sometimes 1 uppercase m is roughly equal to the lowercase 1m. What's the reason? Usually if we are using water as the solvent in a fairly dilute solution, if you use 1,000 grams of water, the final volume of the solution is roughly 1 liter. All right, and then it's just coincidence for water. And then 1 uppercase m, 1 molar, is equal to 1 mole for dilute aqueous solution. All right. In upper level chemistry courses, sometimes we use mole fraction. It's unitless. It's the number of moles of solute divided by the total number of moles of everything in the solution. One very good example is air. Air is a solution. So what's the mole fraction of oxygen? Well, 0.2. What's the mole fraction of nitrogen? 0.78 or 0.79. And then you can look up the mole fraction of CO2, water vapor, and argon in air as well. And then we can convert this mole fraction into mole percent. That's very simple. You just have mole fraction times 100%. So for oxygen in air, it's roughly 20%. Nitrogen, 78% or 79%. Water vapor, it really depends. If you feel it's humid, maybe you have a slightly higher mole percent of water. Percent by mass. All right, this is the mass of the solute divided by the mass of solution. So this is the total mass of the entire solution. So if you're dissolving 2 chemicals, A and B, in water, so it's going to be the mass of A divided by the mass of A and B and water together to get the percent by mass for A. All right, for B, again, you need to have the mass of B divided by the sum of A, B, and water. All right, and then don't forget to time 100% in the end. And then you have part by thousand by mass, part by million by mass, part by billion by mass. They are just roughly the same. What you need to do is, again, mass of solute divided by the mass of solution, and then multiply by 1000 ppt, part by thousand, and 1 million ppm, part by million, and 1 billion ppb, okay, part per billion. So you can do that. Sometimes we mix two liquids, and it's more convenient just to measure the volume of the liquid rather than weighing the liquid. And then there's percent by volume. It's the volume of the solute divided by the volume of the solution times 100%. And also you can have ppt, part by thousand, part by million, part per billion, part per million, per thousand by volume. So again, you just do this kind of multiplication correspondingly. So let's work on some practice problems. Let's say we dissolve 80 grams of sodium hydroxide in 2 kilograms of water. Let's say the final volume of the solution is roughly 2 liters. All right, it's going to be roughly 2 liters. And this volume does depend on temperature slightly. So this is an approximate number. Now let's calculate its concentration in various units. All right, you may pause here and work on this and get this molarity, mole fraction, mole percent, part per million by mass, part per million by volume, but in this case it's actually hard to measure the volume of sodium hydroxide. So now let's look at the answer. The molar mass of sodium hydroxide is 40. Sodium, I think, has a 23 AMU, oxygen 16, hydrogen 1, 23 plus 16 plus 1, that's 40. So we're dissolving 2 moles of sodium hydroxide in this 2 liters of solution. So the molarity is 2 moles of solute divided by 2.0 liters of solution. So it's just 1 molar. Now we can do molarity with the L here. So it's 2 moles of solute divided by 2 kilograms of solvent. The result is 1.00. This is lowercase m molo. And we can calculate the mole fraction. We have 2 moles of sodium chloride and 111 moles of water. How did I get this? Look, we have 2,000 grams of water. And the molar mass of water is 18.02. So you use 2,000 divided by 18.02. I think you will get 111. Then what's the mole fraction of sodium chloride? Well, on top it's 2. On the bottom, it's the total number of moles of everything in the solution. So it's 2 plus 111. Therefore, it's 113. The result is 0.0177. That's the mole fraction. You can convert this to mole percent. It's just 1.77 mole percent. You can do percent by mass, so it's just 80 divided by, again, you need to sum up the mass of solute and solvent. It's 2080, so the result is 3.85. That's the mass percent. And then you can convert this to parts per million by mass easily. All right. Well, again, it's just the same division. This time, you don't multiply this fraction by 100%. You multiply this fraction by 1 million parts per million. And you get this much ppm. You can do ppb, part per billion as well. Okay, this is huge. It's more than 30 million ppb. So that's why units are very important. Parts by volume is rarely used for solute, so because it's not convenient to measure the volume of table salt. Another practice problem, let's dissolve a liquid in water. So let's say 5.0 milliliter pure ethanol with this density. I'm going to dilute this into 1.0 liters aqueous solution of ethanol, okay, by adding water into this. I need to add a lot of water into ethanol. Now let's calculate the concentration of the diluted solution. So first, percent by volume, it's easy. So the volume of the solute is 5.0 milliliter. The total volume in the end, the total volume of the solution in the end is 1000 milliliters over here. Therefore, the volume percent is 0.5%. Parts per million, parts per billion, you can just do this kind of calculations very easily. Now, the density of pure ethanol is 0.79 gram per milliliter, and we started with 5 milliliters. So 5 times this, you get the mass. 3.95 grams of ethanol is dissolved in water. Now we need to estimate the amount of water we used. So ethanol is 5 milliliters. The final volume of the solution is 1000 milliliters. So I'm going to assume roughly 995 milliliters of water is used to make the solution. It's probably slightly greater than this because when you mix water and ethanol, the total volume is slightly smaller than the sum of the volume of the water and the volume of ethanol. But I think this is a fairly good estimate, 995 milliliters of water plus 5 milliliters of ethanol. And the mass of this much water is roughly 995 grams. Again, I'm assuming the density of water is roughly 1 gram per milliliter. Roughly 1. So we can compute the mass percent. That's the mass of ethanol divided by the mass of the solution. Over here, this is water. This is ethanol. The result is 0.395 mass percent. So look at this. This is mass percent. And this is volume percent. So these two numbers differ. You can convert this to ppm, ppb. That's easy. Mole fraction. You need to compute the number of moles of ethanol and water. The number of moles of ethanol is the mass divided by its molar mass. Ethanol is carbon 2, hydrogen 6, O. So carbon 2 you get 24, plus 6 from hydrogen, plus 16 from oxygen. The result is 46. And then we do this division to get the number of moles. It's 0.0857 moles of ethanol. How about water? Well, we have 995 milliliters of water. Assuming the density is 1, we get 995 grams of water. So you can compute the moles of water easily by using this 995 divided by the molar mass of water. That's 18.02, and I think you will get roughly 110 moles of water. And then by using the number of moles of water and the number of moles of ethanol, you can compute the mole fraction and the mole percent. Now finally, let's look at the molarity. Molarity is the number of moles of the solute divided by the volume of the solution. So we have this number of moles of ethanol here divided by 1 liter solution. The result is 0.0857 uppercase M. That's molar. What about molarity? It's the number of moles of ethanol divided by the mass of solvent. So the solvent is, oh, I'm sorry, I got a wrong number here. So 995. All right, so I think I need to modify this number. You need to use the number of moles of ethanol divided by the mass of the solvent. The result, I think, is roughly 0.0853 mole per kilogram solvent. Or you can use the shorthand notation, lowercase m, molo here. Again, if you look at the molarity 0.0857 and molarity 0.0853, they are close to each other because we're talking about dilute aqueous solution. For all dilute aqueous solutions, it's fairly common. 1 liter of solution means roughly 1 kilogram of water is being used as solvent.